Hi folks, and welcome to our third video on our 2-12 lab demos. And this video we'll be discussing demo 3 and demo 4, which involves dissolving salts. And we can tell by this video that sometimes when we dissolve salts, energy overall is given off. Other times when we dissolve salts, overall energy can be taken in or pulled into the dissolving process. To understand how this is possible, the same way that chemical reactions involve a few steps, so does the dissolving of salt. Remember, when a chemical reaction happens, we first have to add energy in to the reaction. There's always an endothermic step. So in a chemical reaction, energy has to go in order to break the reactants apart, so that they can form new bonds. So energy goes in to break the reactants apart, then new bonds form. And as the new chemical bonds form, energy is released. Energy is released because stability is improving as we form these new bonds. Atoms would rather be bonded than not bonded. Now, whether a chemical reaction is exothermic and endothermic overall depends on which is bigger. If it takes more energy to break apart the atoms than is released when those atoms form new bonds, then the reaction's endothermic. More went in than came out, it's endothermic. Why would an endothermic reaction happen? Entropy must be driving it, and that was discussed in our second video. Energy can be given off. If it takes less energy to break the reactants than is given off as the product forms. If more energy is released than was taken in, overall, it's exothermic. Much the same thing can happen with salts. In order for a salt to dissolve, remember, a salt is a regular repeating pattern of ions, a crystal lattice. Positive ions next to negative ions, positive ion, negative ion, positive ion, negative ion. Water has to pull those ions apart. The pulling of those ions out of a salt crystal takes energy. The step of pulling those ions out of the salt takes energy. We discussed why water can do that. Why can water pull apart some salts? The answer is because water is a polar molecule. Remember, oxygen's an electron hogger. Hydrogens have their electrons hogged by the oxygen, making the oxygen on the water molecule act as though it's negative. It's partially negative. The hydrogens on a water molecule are partially positive because their electrons are being hogged by the oxygen. Electrons are negative. If they're pulled away from the hydrogen, that leaves the hydrogens acting like they're positive. So the positive ions, partially positive hydrogen ions, act like pinchers. They grab onto a negative ion, the anion in the salt, and they pull it out. The oxygen on a water molecule is partially negative, so it pulls on a partial positive ion in the salt crystal. Water tries to pull the salt apart, but that takes energy. Once the salt is pulled apart, now those salt ions are free to move around the water. The negative ion in the salt is attracted to the hydrogens on a water molecule. The positive ion in the salt, the cation, is attracted to the oxygen on a water molecule. That attraction, called solvation, that attraction called solvation releases energy. That process is exothermic. So endo to pull it apart. Exo as the ions are attracted to water molecules. If the pulling apart of the salt takes more energy than the attraction to the water molecules, it's endothermic overall. If more energy is being released as the ions are attracted to the water molecules than it took to pull the salt apart, then energy is going to be released. That's exothermic overall. The enthalpy change would be negative. Why would a salt that is harder to pull apart, why would a salt that's really hard for the water to pull apart, takes more energy for the salt to pull apart than is released when the ions mingle with the water molecules? Why would that happen? Because a salt is a gigantic, enormous, rigid, regular repeating pattern, very structured, very ordered. Remember, in the universe, things are tending towards less order, more chaos. Things are tending towards disorder. So the pulling apart of a salt will always increase entropy. Some salts can't be pulled apart by water because the water molecule is not strong enough or doesn't have enough energy to pull it apart. Not all salts dissolve. So in our first demo here, exothermic, calcium chloride. When the calcium chloride salt was pulled apart by the water molecule, the temperature went up. It went from 21 up to 62. That meant energy was being released into the water as the salt was pulled apart. That's definitely exothermic. The water is the surroundings. The pulling apart of the salt is the system. So as it pulled apart the ions from the salt crystal, that took energy. When the salt ions began to mingle with the water molecules, that released energy. It must have released more in the mingling step than was taken in the pulling apart step. Overall, it's exothermic. Our next salt that they dissolved was ammonium chloride. How did they show that this was endothermic? In this one, if you remember, they had a wood block. They put water on the wood block. They put a flask on there with water in it. Then they dumped in the sodium chloride, stirred it up, and the wood block with water on it froze to the flask. That meant energy must have going from the water into the flask. That meant energy was moving in. That's endothermic. The flow of energy was in. Is the dissolving of a salt always exo or endo, or does it depend on the salt? Well, we just saw it depends on the salt. Demo 3 was exo. Demo 4 was endo. Why, though, could it be possible that some salts give off energy when they dissolve and other salts take in energy? Again, there's two steps. There's two steps. If the pulling apart of the salt by the water doesn't take much energy, and energy is released as the ions mingle with the salt, the water molecules mingle with the salt ions, then overall it's exo. If it takes a lot of energy to pull the salt apart and not much energy is released, a lot goes in to pull it apart, not much is released, then it's endo. Why does endo happen when the universe prefers exo? It's because anytime a salt is pulled apart, those ions are now free to mingle. They're out there mingling around. A salt is made up of billions and billions of ions. When it dissolves, the ions, those billion ions, are moving around randomly on their own. That answers number 6. Anytime a salt dissolves, we are increasing entropy. Let's take a look at number 4 to make sure we understand this. For a salt to be exothermic, the pulling apart of the salt must require less energy than the energy released during the mingling, which we call solvation. It says up here, solvation is the attraction of the ions to the water molecules, if water is in fact the solvent. For it to be endothermic, what must be true? The pulling of the part of the salt must be taking greater energy than the energy released as they mingle. It still happens because the salt ions are now free to move, and that increases the entropy. Hopefully that helps you to understand the 2 steps, the processes involved in dissolving, There's energy in to pull the ions out, apart. There's energy released as the ions mingle with the water molecules. If you have any questions on any of 2-12, don't hesitate to email me, contact me, ask me, set up office hours, because this is all important to understanding chemical processes. And then in this case of Demo 3 and Demo 4, physical processes, because dissolving is a physical change, not a chemical change, because the ions are still floating around. Thank you for watching.